From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. I don't know if anyone's forgotten or not, but next week is a vacation week. Have you forgotten that? Or, well, I kind of forgot about it, but anyway, as I said last class, the week after next I will not be here. And so what I'm going to do is next week, next Monday, I'm going to have two tapings in the morning, or I guess it begins at 11 o'clock on Monday, and go to 11 till 12:15, and then 12:15 till what, 12, get this right, 11 to 12:15, 12:45 till 2, I guess is the way it will go. And you're welcome to come to those tapings if you want, but you're also welcome to take the vacation if you want to. And if you don't come to the tapings, the tapes will be shown at the regular class time the week after next. And I'm not sure if the tapings are going to be in this room. They may be in the other room on the other side of the control room. Okay, so I guess that's about it. We had homework due today. I see we have a nice pile of papers here. Well, last class we were talking about Finnell diffraction. And let's go back to that now. And first just repeat a little bit of what we had said last class, and then we'll go on to some new material. So we said we had some aperture over here in a plane that I'll call squiggle and eta. And so there's some aperture here. And we're coming over here some distance to the observation plane. And I guess we used the coordinates here, x and y. And there's a distance z between the two planes. And if we pick a point here in the aperture and a point up here in the observation plane and draw a line between these 2 points, this is what we call distance r01. And remember the whole idea here to the Finnell diffraction was that we had a term that went as e to the ik r01, and we made some approximations in what r01 was. And basically what we were doing, the approximations were, instead of thinking of spherical waves leaving this aperture, we're going to assume that we're far enough away here and a small enough region over here that we can assume that these spherical waves are really parabolic waves. And so going through that, we found that the irradiance, the amplitude first, I should say, the amplitude in this plane, u is a function of xy, went as e to the I k z. So that's just due to phase due to propagating between these two planes. And an I lambda z in the basement here. And then we had an integral over this plane. And so let's say minus infinity to plus infinity. And the fact that the aperture here has some finite size, we could put into the term here that goes as u of squiggle and eta. And then we had e to the I, k over 2z, and we had an x minus squiggle squared, and we had a y minus eta squared. And then we're integrating over the aperture, d squiggle d eta. And so this gives the amplitude for the Finnell diffraction in the plane xy. Now, right at the end of class, I think we wrote this a slightly different way. And we wrote it a couple of ways. We wrote it once as so it looked like a convolution. And I'm not going to write that down again today. But right at the end of class, we made this look like a Fourier transform. And so what we did was we multiplied this out, and we took out a portion here that did not depend upon the variables of integration. And we had that u of x and y was equal to e to the I kz over I lambda z. And then the fact that portion that we could take out was e to the I k over 2z, the x squared plus y squared. And now we're left with the integral, and we still will have the u squiggle and eta, and we'll put here the e to the I k over 2z squiggle squared plus eta squared. And then always run out of space here. So we'll come down here. And see, what do we have left? We have an e to the minus I 2 pi over lambda z. So I'll just put 2 pi over lambda in for k. And in the cross product here, we're going to get a 2, so that 2 is going to go away. And here we have an x, times the squiggle, plus a y times the eta, d squiggle, d eta. And if we think back to Gaskell's class, we of course see we have a nice Fourier transform, and we have a Fourier transform of u, which is going to take into account whatever the aperture function here. It's going to take into account how we illuminate the aperture. And then we have this quadratic factor here, e to the I k over 2z squiggle squared plus eta squared, and then the Fourier transform of that. And so this is what we would call the Finnell diffraction integral. And I'll get out my nice red color here and draw a rectangle around this. Now this is not an equation I expect you to memorize, although you'll probably use it enough that you'll memorize it whether you want to or not. But what I do want you to remember is how we got to this, maybe not all the steps of the derivation certainly, but how we got to this and the approximations that we went through to get to this point. Any questions at this point? Okay. Well, to get to this point, we assumed that we could use a scalar diffraction theory. We assumed we're several wavelengths away from the aperture. But the last thing we did was when we went through this expansion of R01, when we did the binomial expansion, we left the higher order terms out. And so what we assumed, first thing we assumed, was that the next term in the expansion was small enough that we could drop it. And this next term in the expansion went as, if we remember here, it was what we call a b squared over term, I guess. And what that really means is, if we go back and look at the terms here, which I'm sure the interested student will do, we have that we're assuming that z cubed, distance between the aperture and the observation plane, which is much greater than pi over 4 lambda times x minus squiggle squared plus y minus eta squared, and I guess I should square the whole thing, and the maximum value of that. Okay? So we assumed that this was true, so we could drop the next order term in the binomial expansion. And if we were to go through some numbers here, and I'm going to steal some numbers out of Goodman's book. Let's say we have a circular aperture of 1 centimeter diameter. So assume circular aperture of 1 centimeter diameter and a wavelength of 1/2 micron. If we go through the numbers here, that this will imply that z must be much greater than 25 centimeters. But if we go back and we just think a little bit more, what is it that we're really doing when we're making this approximation? And when we go through this expansion, we get all these various terms under the integral. And what we want to do here, what's important to us, is that these other order terms that we're trying to throw away, is that they contribute very little to the integral. And what's happening here, physically what's happening, is that these higher order terms are oscillating a lot, going positive, negative, and they are going to tend to cancel out. And so the higher order terms will not contribute to the integral. And so it actually turns out this is a much more stringent restriction than what we really have to have. And you can really get very, very close to the aperture before you fall into problems with these higher order terms. So in practice here, you almost never have to worry about whether these higher order terms contribute to the integral, and you can almost always assume that Finnell diffraction is a valid assumption here. There's a little more detail on this in Goodman's book, which I'm not going to go through here, but it's basically just the higher order terms are oscillating, and they cancel out when you do the integral. So that's Finnell diffraction. And we're going to, in a little bit here, look at some more examples of Finnell diffraction. But before we do that, I want to spend a little time looking at the approximations that we go through for Fraunhofer diffraction. And so this will take us to section 12.2. And again, for this, I still will follow Goodman's book, although there's tens or hundreds of books that cover this same material very well. So 12.2, Fraunhofer approximation. Well, Fraunhofer diffraction is just it's going to be a special case of Finnell diffraction. And if we go back to our equation we had a minute ago for Finnell diffraction, we had this integral here. And inside here, we're taking the Fourier transform of u times this e to the I, a quadratic phase factor. And for the Fraunhofer approximation, what we're going to assume will be at either the maximum size of the aperture is sufficiently small, or z here is sufficiently large that we could neglect this term right here. So let's just write that down. So we'll say that z is sufficiently large that z is much greater than k squiggle squared plus eta squared over 2, and the max value of this. And so if that's true, we can throw out this term right here. And now we simply are going to get, and I'll write it down in a second, but it's just going to be the Fourier transform of u. So it's a Fourier transform of the aperture times however we're illuminating it. So let's write that down. That u of x and y is, well, I'll keep these terms out in front. Yep. E to the I k z, e to the I k over 2z, x squared plus y squared over I lambda z. Integral then of u squiggle and eta, and then e to minus I 2 pi over lambda z times x squiggle plus y eta, and then integrating over the aperture here. And so, as we said a minute ago, all we have is the Fourier transform of u, which is the aperture times however it is we're illuminating the aperture. And so this is what we would call Fraunhofer diffraction. I'll draw a red box around that. Okay. Now, if we're looking at the intensity, or maybe I should say the irradiance, when we square these phase factors out in front, the constant term plus the quadratic phase factor will drop out, and we're left with some normalizing factor out here. But just then will be the square of the Fourier transform of the aperture. Okay. If we were to go through some numbers here as to see when this is valid, again, I'll steal some numbers from Goodman's book. And he now has an aperture width of 2.5 centimeters. And he now picked a wavelength, changed the wavelength here, of 0.6 microns. And then if you go through the numbers up here, you'll find out that z has to be greater than, much greater than 1,600 meters. So it's a little hard to do that in your basketball court, I guess. But how would you see Fraunhofer diffraction, even for an aperture of this size? If I wanted to do it in my basketball court or my lab or whatever, what would I do? Take a lens, right. This is far away, essentially close to infinity. And so what we would do here is that we would take a lens. So this is our aperture. We would take a lens in here, and it takes infinity. So we really have all these plane waves leaving at all these different angles, and we then will look in the focal plane of this lens. Okay. And we will see Fraunhofer diffraction in the focal plane of the lens. So we can see this very easily in the laboratory. So if I look at this for a second, is this really any different from, well, maybe before I do this, I should go back and I'll say one more thing and then I'll do my next drawing. let's say I have a situation here where I want to find the Fraunhofer diffraction pattern of this aperture. And if I illuminate it with a plane wave, I see a nice Fraunhofer diffraction pattern in the focal plane. What if I illuminate this with a spherical wave? Now, what I'm going to say here is that if I go to the focal plane here, what I will see will be the Fraunhofer diffraction pattern of whatever disturbance I have right here. And so that disturbance is a spherical wave illuminating some aperture. What if I wanted to simulate the diffraction pattern that I would get if I illuminated this with a plane wave? Where would I now look out here? So let me say that again. This gets a little tricky maybe. So what I'm seeing in this focal plane is the Fraunhofer diffraction pattern of this aperture as illuminated with a spherical wave. Can you make a guess? We're not going to prove it, but maybe in a homework problem you do, I don't know, but we're not going to prove it in class anyway. But can you make a guess where I would see the Fraunhofer diffraction pattern for this aperture as it would be if I illuminated it with a plane wave? Yeah, that's right. I'll get some other color here. It will be wherever this lens forms an image of that source. So, say it's that. Okay. So this will be the Fraunhofer diffraction pattern for this aperture if it had been illuminated with a plane wave. Okay. Now let's go one step further. We had this case right here where we got the Fraunhofer diffraction pattern in the focal plane of this lens. Let's say instead of putting the lens on the right-hand side, let's put the lens on the left-hand side. And where would I look for the Fraunhofer diffraction pattern? Well, if I think here for a second, you know, putting it here or here probably doesn't make any difference. And so I still would look, I would look in this plane here. Or if I, you know, illuminated this with a spherical wave, it would be wherever this lens brings the light to focus over here. Now there may be some quadratic phase factors across this plane that's a little bit different, but if I'm just looking at irradiance, this will give me the same as the normal Fraunhofer diffraction pattern. Okay. How would the diffraction pattern change if I didn't draw this right. I wanted that to be F here, F to the lens. How will the pattern I get here, how will the intensity anyway, or radiance change if I take this aperture, everything else is fixed, say I have a plane wave coming in, whatever. How will the irradiance pattern here change if I take this aperture and move it back and forth here? Just guess. We haven't gone through any math. In fact, I don't plan to go through any math in this course to show this. What do you think might happen as I...
Would it be equivalent to making your aperture bigger and smaller, so your pattern would go in and out?
Right. It's going to scale. The size of the pattern here will scale, and the farther away I am, the larger the pattern will be here. Okay. Anyway, so what kind of summarizing here? If we kind of think here for a second, Fraunhofer and Finnell diffraction. If I have an aperture, and if I'm looking at Fraunhofer diffraction, what I'm really, in Fraunhofer diffraction, we've gotten rid of this parabolic shape of the wavefront, and we're just assuming we have plane waves leaving the aperture. Okay? So we are assuming that we are far enough away, the aperture is small enough, that these spherical waves leaving this aperture can be approximated as plane waves. And for the case of Finnell diffraction, now we assume that we're far enough away that these little wavelets leaving here are parabolic surfaces. So the aperture is small enough, we're far enough away that these spherical waves leaving here can be approximated as parabolic surfaces for Finnell or as plane waves for Fraunhofer. And that's all there is to it. Any questions? Ready to go on? So, before we go on, I have to ask you, what time do all the basketball games begin today?
Which time's up? Yeah, which time's up?
Well, in Tucson time. 10 a.m. And it's 8:30, so we have to go faster, I guess, to make it through.
Parabolic waves curve the other way, though, on that plot.
You're looking at them coming to focus here. This is right. So 10 o'clock. So are you going to skip the classes? Am I just fortunate to have had a class at 8 a.m.? So you're coming to class today, or are you going to skip the rest, or are you going to wait until tonight just to watch the one game that counts? Curious. Okay, we're going on to Chapter 13. And Chapter 13 is more on Finnell diffraction. And what we're going to do here is to look at some examples of Finnell diffraction. And at this point, I'm going to leave Goodman's book for a while. And I'm not sure what book I'm going to, but it's contained in a lot of books. It's not one particular one that I'm going to follow. But the first thing we're going to do here is to talk about a thing called Finnell zones. So this is 13.1. Okay. Now, Finnell zones are going to be a very convenient way of thinking about diffraction for circular apertures. And they can actually help you a little bit when you talk about rectangular apertures too. But it's really circular apertures where they help a lot more. And so I drew something on the computer, but I didn't give you a copy of it. I figure it's good for you to actually have to draw something here. So what we're taking here, this terrible drawing, we have a point over here, S, source, S, and we're going to come over here a distance Z1 and put a plane in here. And we're going to look at different regions of this plane here. And then we're going to come over here a distance Z2, and this is going to be our observation point over here, P. Now, in this aperture plane here, we're going to break this up into regions here, circular regions. Radius rho, I guess, is what I'm using here. And if I pick a point out here, which is a distance rho away, and just draw a circle about the center point here, the distance from S to this point Q is R1. And the distance from Q to P is R2. Okay? I'll give you a second to write that down, and I'll drink a little coffee and think about basketball for a minute. So after the last class, one even, I can't remember who it was, came up here and told me about this little poll you have going on ESPN Sports Net or whatever it is. So I signed up for that. I thought that'd be great. But now I realize, at least last time I looked, there were only 4 people signed up. Is that right? 4 people. That scares me to death. It'd be so easy to end up in last place with only 4 people. But I don't know. Maybe I shouldn't have done this. But at least it didn't cost any money. At Waco, it used to cost $5. And never won that. So anyway, you have your diagram here. Okay, so now what we're going to do is we're going to look at these distances here. So I'll move that aside. And a distance SQP, so from the source to point Q to point P is R1 plus R2. Okay, bring this back a second. So R1 plus R2, and that's equal to the square root of Z1 squared plus rho squared plus the square root of Z2 squared plus rho squared. Okay. And of course we're going to assume that we're far enough away and the region on here is small enough that we can approximate this as the way we normally approximate spherical waves, as parabolic waves. So that's Z1 plus Z2 plus 1/2 rho squared 1 over Z1 plus 1 over Z2 plus terms that we're going to forget about. So we have this parabolic waves here. Now what we're going to do is that we're going to take this aperture and we're going to divide it into circular zones here. And so I'll write this down. Divide aperture into regions bounded by concentric circles where rho is equal to a constant, but defined such that R1 plus R2 differs by 1/2 wavelength from one boundary to the next. Okay? So we're dividing this into these little zones here where the path length, R1 plus R2, changes by 1/2 a wavelength and going from one boundary to the other boundary. Okay? And we're going to call these regions Finnell zones. So regions are called Finnell zones. Okay? So we can write here that n lambda over 2 is 1/2 rho sub n squared 1 over Z1 plus 1 over Z2. So if we go out here to the rho sub n, we have that the OPD, or the path length I should say, has changed by n half waves. Okay, so right along the axis, the path is Z1 plus Z2. Now we go out some distance, rho sub n, and the path is changed by n half waves. Okay. And so this says that rho sub n, the radius to the nth Finnell zone, is equal to square root, well, I'm going to call it square root of n lambda L, where L is 1 over Z1 plus 1 over Z2, 1 over that. Okay, so I just solved here rho sub n. Okay, and to the first zone, square root of lambda L, n is 1. Second zone, 2 lambda, square root of 2 lambda L, and so on. Okay. Now, one more thing we might look at before we go to the next topic here is that, let's say that we look at 2 consecutive zones and the edges here. So if, say, rho sub n and rho sub n plus 1 are inner and outer radius of the nth zone, then area pi rho sub n plus 1 squared minus pi rho sub n squared. Well, let's see if we come back here. Rho sub n plus 1 squared would be n plus 1 lambda L, and rho sub n squared is n lambda L. And so that's equal to pi rho 1 squared, independent of n. So what we have here is that the areas of all these zones are equal. Okay, that's kind of interesting. We'll make use of that in a little bit. Now maybe I'll put down here a little note. If, keep higher order terms. The areas actually increase slightly. Oops. As rho increases. So, I mean, this is just a little note that we'll remember, but won't worry much about, I guess. So, to within the approximations that we like to use, assuming these are nice parabolic waves, the areas of all these zones are equal. So if I just happen to bring a drawing here, one that you've seen many times in the past, this is what the zones would look like, where every other zone here I've made opaque in this. Or Edmund Scientific made every other zone opaque here. So I actually had lunch yesterday sitting next to Mr. Edmund of Edmund Scientific. Told him how great I loved his drawings here. Question?
Worse as you move out in that pattern as rho gets bigger then?
The areas, as we move out from here, the areas will slightly increase. The approximation that, of, the parabolic approximation that we make gets worse as we move out here. But it doesn't get worse very badly. Don't lose any sleep over it. Well, it's not, I mean, if I count the number of Finnell zones, I don't know how many there are here. There aren't that many, actually. So it's probably not bad here. Yes?
Adding
Yeah, they look the same. We've had, I mean, this is the same pattern that we've seen all along. We interfered a plane wave and a spherical wave, or a couple of spherical waves looking in the right direction anyway. I mean, this comes up all the times in optics. In all areas of optics, not just in optics 505. You see it a lot. Okay, so these, what we're now calling these things, are Finnell zones. I've made every other Finnell zone dark, and later we'll see why you might do that. And but right now, I just want you to remember that the path length in going from one edge, one Finnell zone to the other, or one edge to the other, the path length changes by half a wave. And the other thing to remember is that the areas of all these Finnell zones are equal to within the approximations that we're making here. Okay? So you might say, so what? Well, let's keep going. So 13.2. And this will be a circular aperture we're talking about here. And so, similar to what we had before, just draw it here. Source S, point P, and we're going to have an aperture in here that's supposed to be circular, and you know, Z1 away again from the source, Z2 away from the observation point. We'll pick a point here. In the aperture, and so that's R1 away, just like before, and R2 away. And this guy has a radius here up to that point of rho, and here kind of the strange thing. I don't know why I've done this, but the radius of the aperture is C. Why I ever picked that, I don't know, but it's what I have in my notes, so I'll go with it. Radius of aperture equals C. And then we're going to assume, of course, that C is much, much less than Z1 and Z2. Okay. We're going to assume angles small, so we can neglect the cosine factors in the Finnell diffraction integral. And we're going to make all the normal assumptions. Okay, so we can write down, now the other thing, what we're doing in this section here is that we're only going to look at a point on axis here. Only going to look at a point on axis. But we're going to, by doing that, we're going to learn something here pretty neat, I think. So we can say that U naught on axis, point P, and that's equal to, well, amplitude of what we're illuminating the aperture with. We get the A from that. We get the I, Z1, and a Z2, a lambda. And the integral here e to the I, k, R1 plus R2. And we want to integrate over this aperture, so that's what, 2 pi rho d rho, and rho goes from 0 to whatever this crazy radius was, c. Okay. So that's just our normal Fresnel diffraction formula where we've made our normal approximations and threw away the cosine factor here. Set the cosine factor equal to 1. Okay, so now we want to play with this a little bit to see what the irradiance is on axis. And so first, well, as always, R1 squared, Z1 is equal to Z1 squared plus rho squared. And R2 squared is Z2 squared plus rho squared. I think that pen is wearing out. Switch to this one. And so if I take derivatives here, we would have rho, d rho is, well, Z1 constant, and so that's R1 dr1. And if we took the derivative over here, then rho d rho would be R2 dr2. Okay. So playing with this a little bit, d r1 plus r2 is 1 over r1 plus 1 over r2 rho d rho. Yes?
The old differential elements. Isn't there a 2 in front of that somewhere?
Right. When I take the derivative, there's a 2. I get a 2 rho d rho, but that's equal to 2 r1 dr1. So I just cancel the 2's. Okay. Well, I have to play with this a little bit more. I want to get this in a form that we can write down the answer for. So the next thing we could say is, or rho is equal to R1 R2 over R1 plus R2 d R1 plus R2. Okay. Now we're going to approximate here that R1 and R2 here are almost Z1 and Z2. So we can say this is approximately equal to Z1 Z2 over Z1 plus Z2 d R1 plus R2. Okay? Question?
1 plus R2. You're considering R1 plus R2 to be a single?
D of R1 plus R2, right. So I had, I'm just adding these up here, solving for dr1 and dr2 and adding it.
You're integrating as though R1 and R2 was a single term?
Well, I have a dr1, so I'm saying this is dr1 plus dr2. So now we'll take this and plug it in up here. And so what we have, I guess I have to move that out of the way. So, therefore, U naught of P is equal to, well, to factor out the 2 pi, so 2 pi A over I lambda. Now when we multiply through by here, the Z1 and Z2 will cancel this one, and then getting a Z1 plus Z2. So Z1 plus Z2. Integral here And I don't know what the limits are right now, but we'll worry about it in a minute. E to the ik, R1 plus R2. And the rho d rho we've replaced with a d, R1 plus R2. And now we have to think here, the limits of this. Well, the limits here on rho went from 0 to c. And so limits here will go from dr1 plus r2 will go from z1 plus z2 to, I don't know what this is up here, goes up to r1 plus r2 when, whatever that is, when rho is equal to c. Don't know what it is. Okay. So it goes from z1 plus z2 to whatever r1 and r plus r2 is equal to when rho is equal to c. Okay. Now we're going to say r1 plus r2 is equal to z1 plus z2 plus something. I don't know what it is. That's something, that's some number. And I'm going to write that number as q, some number, times lambda over 2. Okay? So r1 plus r2 is z1 plus z2 plus some number, which may or may not be an integer, times half wave. So you buy that? Okay. So now we can write this integral here as, well, let's see, u naught of p. Well, I'm going to keep my I down here in the basement. I'm going to keep my pi up here. And if I think here for a second, before I finish this, fill this out, let's think here for a second. I could say that u double zero of p, which is the irradiance, which is the amplitude I would have at this point if this aperture were an infinite size. So u double zero p is the unobstructed amplitude at point P. And that would be, you know, if I have this spherical wave over here coming out here, and so the amplitude I'd have at that point would simply be a e to the I k times the distance, z1 plus z2, divided by the distance, z1 plus z2. Okay? So I could say that u double zero p is what I would have if, you know, I had an infinite size aperture, and that's just a e to the I k, z1 plus z2 over z1 plus z2. Now this is only on axis. I'll repeat that again. We're only looking at this on axis. Okay, so now I can come up here to what I had, and I look here for a second, and I see that I can rewrite this as u double zero of p times integral of e to the I pi q dq. So I've taken e to the I 2 pi over lambda r1 plus r2, and I got a 2 pi over lambda z1 plus z2, so that came into my u double zero p, and all I'm left with is 2 pi over lambda times q times lambda over 2. So that's e to the I pi q. And dr1 plus dr2, well, this is a constant, so that's just dq times lambda over 2. And so that lambda cancel that lambda, and that 2 cancel that. And so I'm left with this. Well, now q goes from, well, right on where R1 plus R2 was right on the axis here, Z1 plus Z2. That goes to 0. And up here, oh, I still don't know what it is up here. Squiggle, okay? Where squiggle is equal to Q for point on the rim. Okay? Don't know what it is. Maybe an integer, may not be an integer, some number, that's all I know. Okay? Anyway, so we've gotten that far. Let's keep going here. So now here's an integral that with your help I can do. Okay? And so we would have that u0 of p is equal to u00 of p times 1 minus e to the I pi squiggle. Okay? That worked out pretty nicely. And so I could rewrite here that the irradiance at point P, maybe I should put a 0 there, but I'll leave it off. Radius at point P is equal to 2 times whatever the irradiance would be if I had an infinite size aperture, times 1 minus cosine pi squiggle, whatever that is. And so that's equal to 4 I00 of p times the sine squared of pi squiggle over 2. And I should draw a box around that. And I'll celebrate by having a sip of coffee. So what this is saying is that if I take this aperture here, okay, and now as I change the size of the aperture, the irradiance at this point is going to go between 0 and 4 times what the irradiance would be if I just had an infinite size aperture here. So let's write that down. That's kind of neat, actually. I think, anyway. So we say, therefore, as radius of aperture increases, irradiance at P oscillates between 0 and 4 times the unobstructed irradiance. So isn't that kind of neat? I don't know. I think it's neat. Anyway. So by putting this little aperture in here, you may get no light there, or you may actually increase the amount of light there by an amount equal to 4 times what you had before. Well, how much light we have there depends upon this thing squiggle, and I still don't know what squiggle is, so we can't stop yet. We have to keep working. Okay. What is squiggle? So let's look at the relationship between squiggle and the aperture radius C. Okay, so now what we can say, we had before that R1 was equal to Z1 squared plus C squared, square root of that. And we said that was about Z1 plus C squared over 2Z1. And we also had that R2 was about Z2 plus C squared over 2Z2. Okay? And so what we have here is that R1 plus R2 is Z1 plus Z2 plus squiggle lambda over 2. And so now we can say that squiggle lambda over 2 is equal to, from up here, just C squared over 2 times 1 over Z1 plus 1 over Z2. And so then we can solve that for squiggle. And we have that squiggle is equal to C squared Z1 plus Z2 divided by lambda Z1, Z2. So now we know what squiggle is in terms of C and Z's and lambdas. Now let squiggle equal 1. If squiggle is equal to 1, and we think about back in terms of the Finnell zones, if squiggle is equal to 1, that means we have only one Finnell zone present. Then only one Finnell zone present. And then I of P is equal to 4I, what did I use, 00? 00 of P. So the result is that the intensity produced by the first zone is 4 times the intensity obtained with a clear aperture. So therefore, I'll say irradiance produced by first zone equal 4 times irradiance obtained with a clear aperture. Okay. So if we have one zone present, one Finnell zone present, we get 4 times what we would have with a clear aperture. If we have 2 Finnell zones present, we get 0. Okay. So with an odd number of Finnell zones here, we're going to get 4 times. Even number, we're going to get 0. Now, if you think about that for a second, let's go back here. Let's think here. So here's all these Finnell zones we had. And I went to the secretary to get some black paper, and this is the closest thing I could get to black paper. I don't know. Works, I guess, anyway. You know, if we just have one Finnell zone present, we're getting 4 times what we'd get if we had a clear aperture. If we had 2 Finnell zones here, we're getting nothing. And the reason for that, I mean, think physically. First, the area of each one of these Finnell zones is equal. And I go from here to here, you know, I change by pi over 2, by pi. And I go from here to here, I change by another pi. So if I had 2 Finnell zones present, for every point in the first Finnell zone, I would have a point in the second Finnell zone that would be out of phase by pi. And so they're going to cancel. And so now if I have 3 Finnell zones present, well, 2 of them will cancel one another, and I'm left with 1 again. And so I'm back to 4 times what I would have with a clear aperture. So these Finnell zones are kind of a neat way to think about how this aperture is built up here. Okay. Just think of the different Finnell zones canceling out one another. If you have an even number, it's all gone. If you have an odd number, you have 1 Finnell zone left. Okay. And if you think of a lens, you know, if I put a lens over here, well, what I'm really doing is that by the thickness of the lens, I'm changing the phase difference between these different Finnell zones, and some way I'm keeping the light from canceling out. Okay. Understand that? What if I moved off axis? I looked here only at a point on axis. I did that because the math was easy. What if I move off axis? It's no longer so easy. But if I think of moving off axis, I still have these Finnell zones, but now instead of picking a centered portion, I have some off axis portion here. And now some way we have to add up all these portions of these Finnell zones to see how much light we have left. Okay. So you're an expert on Finnell zones, and you're an expert on using Finnell zones to look at circular apertures and finding out how much light you have on axis anyway. And yeah, I want you to not only understand the algebra here, but to understand the physically what's happening. Okay, ready to go on? And you ready to go on to something that's absolutely amazing? Even more amazing than the circular aperture. And that's the opaque disk. Okay, so now instead of having source, point, aperture, what we're going to have is source, point, obstacle. Okay? And we're going to look right on axis here and let U0 prime of P equal amplitude at center of pattern for opaque disk. Okay. What do you think you're going to get on axis here? And those of you who have read books or anything like that aren't allowed to answer, but just guessing, what do you think you're going to have on axis? No one wants to guess. Huh? Yeah, okay. And so we would have that U0 prime of P. Well, I don't know how to solve this, but we already have solved this one. And so what principle might we use to go from here to here? Babinet's principle. Good. Okay. And so U0 prime of P, which is what we have here, is equal to whatever we would have there if we had an unobstructed, or if we had a clear aperture, just say. Minus what we would have here with the hole. And someplace back here, I don't know if I can find it right this second. Here's what we had with the circular aperture. So I'm going to take U00P and subtract this from it. And what do we get? We get U00P times e to the I pi squiggle. Okay? And so I prime of P on axis here is equal to I00 of P. Simple as that. Amazing. So what we're getting here right on axis is the same thing that we would get if we took this away. Now, isn't that amazing? Let's write that down. It's so amazing. Therefore, at center of shadow, for, well, we'll say in the case for squiggle, not too large to make above approximations. Invalid. We have a bright spot that has the same irradiance as the unobstructed value. Okay. So needless to say, if we were to move our point right up here, right at the obstacle, we wouldn't have this irradiance, and that's where all these approximations have broken down. But if we move out here far enough that their approximations are valid, we're going to see that as we move along here, we always have the irradiance that we would have if the obstacle were moved away. And this is a neat little experiment to do in a lab. You put, well, maybe for the obstacle you use a ball bearing, or I've used a penny. And you honestly see that bright spot. I mean, it's fantastic that you have that. Now, as the obstacle becomes larger and larger, on axis the irradiance doesn't change, but if you go off axis it changes faster, and I mean it changes rapidly. And as the obstacle becomes large, you contain less and less light here, but right on axis the irradiance remains the same. How many have done this experiment? One. Only one. I don't know. I think next year when I teach this course I'm going to have a couple, have to throw in a couple of 3 experiments. Something like this is something that you all should see because it's so absolutely amazing that it works. Okay, well, while, as I said, 2 weeks from now I will not be here, and you do have homework due 2 weeks from today, isn't that right? And so I'm still expecting you to hand in the homework, and I'm looking for a volunteer who will come to class 2 weeks from today and pick up the homework and put it in an envelope and put it in Jim Gleason's mailbox. Can each put it in his mailbox? Do you want to do it that way? Okay, so I have 40 volunteers who are going to do this now. And you all put it in poor Jim Gleason's mailbox, okay? Okay, well, have a good vacation, and maybe some of you I will see here next Monday. And I hope you think a lot about interference and diffraction over the vacation, but I also hope you watch 1 or 2 basketball games. And I hope that next time I see you, we are still in the tournament, okay?